Hello everyone. Welcome you all to week 12 problem solving session for the course Introduction to Group Theory. I'm Priyanka Sharma, your PMRF NPTEL teaching assistant for the course. In today's session, we will learn the structure theorem for finite abelian groups. Before starting this, first we recall some basic terminologies. So suppose we have a group G and A and B be two elements in it such that they commute. And if order of A is M and order of B is N, then GCD and GCD of M and N, if that is 1, then the order of AB, that is order of the product of these two elements, will be the product of their orders. And let G be a finite abelian group and order of G is N, if maximum of order of elements in G is D, that is D is maximum of this set where we have order of X, where X belongs to G, then order of G divides this maximum order D for all elements G belongs to G. And this D, which is the maximum possible order in the given finite abelian group, this is known as the exponent of G, and it is denoted by either E of G or exponent of G. So now we can say if order of two cyclic groups are relatively prime, then their product that will again a cyclic group, that is Z mod NZ cross Z mod MZ. This will be isomorphic to Z mod NMZ if GCD of these two numbers N and M is 1. We can generalize this statement into this form. That is, if we have k natural numbers, say M1, M2 up to Mk, and they are relatively prime or the GCD is 1, then the product of Z mod MIZ, this will be isomorphic to Z mod product of MIZ. Similarly, we can have this result for this prime factorization form. So if we have a natural number n and we express this into its prime factorization form, that is n is p1 to the power alpha 1 into p2 to the power alpha 2 up to pr to the power alpha r, then z mod nz, this will be isomorphic to z mod p1 to the power alpha 1 z cross up to z mod pr to the power alpha. So these are some basic results which we have already discussed in previous session. So based on this, we can define the structural theorem for finite abelian group. So this is a version where we are using invariant factors. So suppose we have a finite abelian group G and order of G is n, then there uniquely exists this invariant factors H1, H2 up to HR satisfying these three conditions. That is, HI is a cyclic group for all I between 1 and R, and G is isomorphic to their direct product. That is, G is isomorphic to H1 cross H2 up to HR, and order of HI plus 1, these divides order of HI for all I between 1 and R minus 1. Okay, it means whenever we express this G as the direct product of invariant factors, then these factors have two conditions. That is, every factor is a cyclic group, and order of the cyclic group which is appearing later will divide the order of previous cyclic groups. Okay, that is here order of H2 will divide order of H1, order of H3 will divide order of H2, and so on. That is the third condition. Now, Okay, so this version is for direct product. So if the finite abelian group is like this, we have G plus, we have an additive abelian group, so we can have an alternate version of this. Here, G can be written as the direct sum of HI. Also, if order of HI is MI, then order of G is product of MIs, and MR divides MR minus 1, which divides MR minus 2, up to M2 divides ME. Okay, and order of E is order of H1. Okay, so what is H1? H1 is actually the first factor or the first cyclic group appearing here, and this E is the exponent of. So, yeah. Uh, okay, so now we have first version of structure theorem for finite abelian group. Zoom it up, right? Um, Let G be a finite abelian group, then G can be expressed as a direct product or direct sum in case we are dealing with an additive abelian group. So G is a direct product of cyclic groups of prime power orders. That is, G is isomorphic to Z mod P1 to the power E1 Z cross Z mod Pk to the power Ek Z, where this PIs are some prime numbers and they are not necessarily distinct. They can be same also. Moreover, this prime powers, that is P1, E1, P2, E2 up to Pk, Ek, they are uniquely determined by the given group G. Now, what is the meaning of uniqueness here? So suppose G is written as this direct product form, that is G is isomorphic to Z mod P1 to the power E1 Z cross up to Z mod Pk to the power Ek Z, and G is isomorphic to this group as well, which is Z mod Q1 to the power L1 Z cross up to Z mod Qk dash to the power Lk dash Z. Here again, Q1, Q2 up to Qk dash, they are prime. Then for the uniqueness, what we have, there exists some permutation sigma from Sk such that K and K dash, they are same. That is both the forms, this one and this one. The number of groups, they are same. That is K and K dash, they are same. And Qi to the power Li, this is same as P to the power sigma I, uh, P sigma I to the power E to the power sigma I. For all I equals to 1 up to K dash. That is, these factors are same, but they are permuting. Okay, it means this form for the finite abelian group G is unique up to reordering of these factors appearing in its direct product form. Now we have an example to explain this. So suppose n is 162. So first we break it into prime factorization. So this is 2 into 3 to the power 4. Then the number of abelian groups of order 162 up to isomorphisms are this. So the number is 5. And what are those abelian groups? So first one is the cyclic group, that is Z mod 162Z, which is as isomorphic to Z mod 2Z cross Z mod 3 to the power 4Z. So yeah, clearly here 2 and 3 to the power 4, they are co-prime. So we can write them combinedly to 162 here. So this is the only cyclic group of order 162. And remaining 4 will be non-cyclic, but abelian groups of order 162. So second one can be Z mod 2Z cross Z mod 3 square Z cross Z mod 3 square Z, which can be written as Z mod 18Z cross Z mod 9Z. So here we can see that this 2 and 3 square, they are co-prime. So we can write them combinedly to this, and this Z mod 9Z, this will be the second one. And similarly, we can have this Z mod 2Z cross Z mod 3Z cross Z mod 3Z cross Z mod 3 square Z, which is isomorphic to Z mod 18Z. So what we have done here the highest power of 3 which is appearing is 3 square. So this 3 square is co-prime to 2. So we combine the first and the last group in this direct product form. And combinedly, we have written Z mod 18Z for that. And the remaining part is Z mod 3Z, Z mod 3Z. So now we can't club them because 18, 3, and 3, they are not co-prime. So this will be isomorphic to this. The fourth possibility for abelian group of order 162 is Z mod 2Z cross Z mod 3Z cross Z mod 3 square Z. So similarly, here this 3 cube is the highest power of 3 appearing in this direct product form. So we club this with this Z mod 2Z because here 2 and 3 cube, they are again relatively prime. So the first factor will be Z mod 54Z and the second one will be Z mod 3Z. Lastly, we can have this Z mod 3Z cross Z mod 3Z whole power 4, that is Z mod 3Z is appearing 4 times in the direct product form. So again, in all last 4 factors, power of 3 is same, that is 1. So we can club only Z mod 2Z and Z mod 3Z, and that will be Z mod 3Z, Z mod 6Z, and we have remaining 3 factors as. So we can notice here that number of non-isomorphic abelian groups of order 164 is the product of partition of the powers of prime numbers which is appearing in the prime factorization form. So here in 162, we have 2 to the power 1 and 3 to the power 4. So what will be the number of non-isomorphic abelian groups of order 162? That will be partition of 1 into partition of 4. Now, what is the meaning of partition? So partition of R, uh, uh, in partition of R, we mean we have some lambda I, say lambda 1 to the power lambda A, all are greater than 0 such that they sum to the number R whose partition is being taken here. Now we have another version of structural theorem for finite abelian group. So this version is motivated by the clubbing which we have done here. Like the highest power of 3 and the corresponding group, which is Z mod, say 3 to the power IZ, that was clubbed with Z mod 2Z. So this is the motivation behind the second version of structure theorem. So if we have a finite abelian group, say G, then G can be written as Z mod AZ cross Z mod A1Z cross up to Z mod AMZ, where AM divides AM minus 1, AM minus 1 divides AM minus 2, up to A2 divides A1. That is, here, if we have this number AI, so we can say that each number I divides its previously appearing number AI minus 1 in this direct product form. And all these AIs are uniquely determined by the group G. Note that if we have two finite groups, say H and K, then H cross K, this is isomorphic to K cross H. Okay, so that's why in the form of G up to isomorphism, uh, by uniqueness we mean uniqueness up to reordering. Okay, and if we have a finite abelian group, say G, and H and K, they are subgroups of G, then followings are equivalent. That is, G is isomorphic to H cross K, and G is HK, and H and K, they are disjoint. And order of G is order of HK, which is same as order of H into order of K. Third result is, let G be a finite abelian group and M belongs to N, that is M is a given natural number, then HM, which is this group, X belongs to G such that order of X divides M. This is a subgroup of G. That is, if for a finite abelian group and a given natural number M, we collect all those elements of G whose order divides the given fixed number M, then we will have a subgroup of G. So here we have an example to understand the structure theorem for finite abelian group in more detail. So suppose we have this form, z mod 7 to the power 4 z cross z mod 3 square z cross z mod 5 z cross z mod 7 square z cross z mod 5 cube z. So this can be written as this form, z mod a1z cross z mod a2z. So here a1 is 7 to the power 4, 5 cube 3 square. Actually here 7, 3 and 5, they are co-prime. So any powers of 7, 3 and 5, they will be co-prime. So what we can do here, uh, here we can again club the factors appearing here such that for the first group, that is Z mod A1Z, here we are choosing this A1 such that this A1 consists of highest power of 7, highest power of 3, and highest power of 5, which are 7 to the power 4, 5 to the power 3, and 3 square. Then the second factor in the direct product form, in that we will exclude the factors in this form which we have already included, and from the remaining factor again we will consider the highest power of 7, 5 and 3. So they are here 7 square and 5. So A2 will be 7 square into 5. So this is how here we have two groups in this direct product form. They are Z mod A1Z and Z mod A1Z and Z mod A2Z, and they are this. Let G be a finite abelian group, then we define M, which is exponent of G, which is the maximum possible order of elements in G. Then order of X divides M, that is order of any element that will divide order of exponents in G. And if G is a finite P group, that is order of G is some power of this prime P, and G has a unique subgroup of order P, then G will be cyclic group. Next result is, if G is a finite P group and H is generated by A, where order of A is exponent of G, then there exists some subgroup K of G such that G is isomorphic to this subgroup generated by A, that is H, cross this group K. So now we have the form of structure theorem for finite abelian group for a P group. That is, if G is a finite abelian group whose order is P to the power E, then Z can be written in this form. So G will be written in this form. So G will be isomorphic to Z mod P to the power beta 1 Z cross Z mod p to the power beta 2z cross up to z mod p to the power beta r z. So obviously in all the factors here, we have p to the power beta I, where we have this relation that is beta 1 is greater than beta 2, which is greater than beta 3, and so on up to beta to the power r. And they all are greater than or equal to 1. So obviously, this is because order of z mod p to the power beta r z, that will divide the order of z mod p to the power beta r minus 1 z. So that's why we will have this relation here. And the sum of all beta i's, they will give us the power of p in the order of group G. Or we can say that this B1, B2 up to BR, this is a partition of E, and this is uniquely determined by the given group G. Okay, so based on this discussion, we will have some problems. So the first question is, find number of abelian groups of order 108 up to isomorphisms. So how to do it? Say n is 108, that is the given order. First, we will write this 108 in prime factorization form. So this will be 2 to the power two, and then we have 3 to the power okay. So it means we have two primes, that is P1 is 2 and P2 is 3, and say R1 is 2 and R2 is 3. So now we will consider the partition of their powers. So what is partition of 2? Here we are considering partitions of R1 and R2, not P1 and P2, although they are same. So 2 can be written as 2 and 1 plus 1. So partition of 2 is 2. And what is partition of 3? So 3 can be written as 3, 2 plus 1 and 1 plus 1 plus 1. So partition of 3 is 3. So number of abelian group of order 108 is partition of 2 into partition of 3, that is right, this 2 into 3 or 6. So we will have 6 abelian groups of order 108 up to isomorphisms. Now, what will be those abelian groups? So for that, we will consider this partitions. So the non-isomorphic abelian groups of order 108 are. So now we will write it using partitions of 2 and partitions of 3. So first, we will consider first partition of 2, that is 2. And here this 3, this is partition of 3. So corresponding to this, we will have this group Z mod 2 square Z cross Z mod 3 cube Z. And this will be isomorphic to Z mod 108 Z. So this is first one. Second one, we will take the first partition of 2, that is this one. And we have used this, now we will use this one, 2 plus 1. So corresponding to this, we will have a second abelian group, which is Z mod 2 square Z cross. Now we will split the power of 3, which is 3 uh, into these two parts. First, we will use power of 3 is 2, and here we will take power of 3 is 1. Okay. So this will be Z mod 3 square Z cross Z mod 3Z. And if we want to write the second version of the structure theorem, so we can club these two. That is Z mod 2 square and 3 square. Why? Because these two are relatively prime. Cross Z mod 3Z. Third one, for the partition 2 of 2, we have another partition of 3, that is 1 plus 1 plus 1. So for here, we will have this Z mod 2 to the power 2Z cross Z mod 3Z cross Z mod 3Z cross Z mod 3Z, corresponding to the partition 1, 1, 1 of 3. And this is isomorphic to Z mod 2 square, which is the highest power of 2 appearing here, into 3, which is the highest power of 3 appearing in this direct product form. Nice. Cross Z mod 3Z cross Z mod 3Z. Now, we have used all the 3 partitions of 3 for this partition of 2. Now we will use this one. So fourth group will be 1 plus 1, and we will use the first partition of 3, that is 3 itself. So for this, we will have Z mod 2Z cross Z mod 2Z cross Z mod 3 to the Z mod 3Z, which is isomorphic to, again, we will club the highest power of 2 and highest power of 3. So we can club these two. We will have Z mod 2 into 3 cube Z cross Z mod 2Z. Okay. Fifth one, we will have 1 plus 1, and here we will have 2 plus 1. So for this, we will get this group Z mod 2Z cross Z mod 2Z cross Z mod 3 square Z cross Z mod 3Z. Okay, which is isomorphic to. So first we will consider highest powers of 2 and 3. That is this one and this one. So we will have 2 into 3 square Z cross. Now we will consider the highest power of 2 and 3 in the remaining factors. That is Z mod 2 into 3 Z. Now we have the sixth non-isomorphic abelian group of order 108, which is corresponding to the partition 1 plus 1 and 1 plus 1 plus 1. That is Z mod 2Z cross Z mod 2Z cross Z mod 3Z cross Z mod 3Z cross Z mod 3Z, which is isomorphic to Z mod 2 into 3 Z cross Z mod 2 into 3 Z, and we have a remaining factor which is Z mod 3Z. So here in all the groups, we can see that uh, the factor which is appearing later in this prime factorization form, that's order is a divisor of order of its previous factors in this form. Okay. So these are the 6 abelian groups of order 108 up to isomorphisms. So what is the solution? Number of abelian groups of order 8 up to isomorphisms is 6. So come to the next question. What is the exponent of the given abelian group here? Recall that what is the exponent of finite abelian group. So exponent is the highest possible power uh, of any order in the given abelian group. So here, given group is Z mod 2Z cross Z mod 4Z cross Z mod 3Z. Let A, B, C, uh, say this is G. So elements of this group G will be of this form A, comma B, comma C, where A belongs to Z mod 2Z and B belongs to Z mod 4Z and C belongs to Z mod 3Z. Here, all the three groups, that is Z mod 2Z, Z mod 3Z, and Z mod 4Z, are cyclic groups. So what will be the possible highest power of elements in this? That will be the order of the group. That is corresponding to the generator of this group. So maximum possible orders in Z mod 2Z, Z mod 4Z, and Z mod 3Z are 2, 4, and 3 respectively. Therefore, the exponent of G is, say, some x comma y comma z, where order of x is 2, order of y is 4, and order of z is 3. Exponent is actually the highest possible order, no? So the exponent of G will be order of this element. So that exponent of G will be order of x, y, z, which is the LCM of order of x, order of y, and order of z. That is LCM of 2, 4, and 3, which is 12. So this is the exponent of the given group. Now come to the next question. Suppose we have two finite abelian groups and they both are cyclic actually, and they are Zn and Zm. Uh, and we are considering this type of function, that is f, which is from Zn to Zm. And this is given by f of x is ax, where this a belongs to Zm. Then this function f will be a homomorphism if and only if the product of the order of this group, that is n, and a here, that is the element of Zm which is defining the function, their product is congruent to 0 modulo m, where this m is the order of the like 4-domain group. Okay. So this is an important theorem which is used to find the homomorphism between Zn and Zn in general set. So how to do it? First, let f from Zn to Zm given by fx is ax for some a belongs to Zm is group homomorphism. Then we will prove that NA is congruent to 0 mod n. So how to do that? So since F is a group homomorphism, we have a condition that corresponding to this, F of identity is identity. If F is a function from G to G dash, and that is a homomorphism. So from this, we will have F of 0 is 0. That is 0 is f of 0, which is now this 0 is identity element in Zn. So we can write like this: 1 plus 1 plus 1 up to n times because 1 is a generator of Zn and order of 1 is n in Zn. Let me write it. Order of 1 is n in Zn. Okay. That is 0 is this will be f of 1 plus f of 1 n times, since f is a homomorphism. So 0 will be n f of 1. Now, if we say this is equation 1, then f of 1 will be a into 1 or a. So we can conclude that NA is congruent to 0 mod M because NA is now an element of Zn. Okay. Conversely, let NA is congruent to 0 mod M. Okay. And we want to prove that this f of x defined by ax, this is a homomorphism. So okay. So if we want to prove that f from Zn to Zm is a homomorphism, that is, we are willing to prove that f of xy is fx plus fy. Okay. So let x and y belongs to Zn. Then x plus y, that is an element of Zn also. And we need to use this condition there. So simply use the Euclidean algorithm here for given n. We have x plus y is nq plus r, where this r, just reminder, this will be greater than or equal to 0 and this will be less than this n. Fine. So now what will be this f of x plus y? This will be f of nq plus r and this will be nq plus r into A, which is the given form of A, that is, okay. Mhm. And by f of x is ax is a homomorphism. So this is the definition of the function actually. Mhm. Yep. Actually, Zm is abelian, so we can write it. Now this will be NAQ plus RA, which is congruent to RA since NA is congruent to 0 mod n. So this will be congruent to RA in modulo n. Now we put the value of R from this. So this will be same as x plus y minus nq a mod m. So this is x a plus y a, and this one will be n a q. So under modulo m, this will be 0. So we have only this. So xa or ax, so this will be f of x and this will be f of y. That is f of x plus y is f of x plus f of y for all x and y belongs to Zm. So we can say that f is a homomorphism. Okay. So yeah. It means a function from Zn to Zm, which is given by this f of x is ax, this will be homomorphism if we have this condition, that is Na is isomorphic to 0 mod n. Now, what does this congruency mean? So, or let me write it as a remark. Congruence Na is congruent to 0 mod m. This has GCD of n and m solutions. So if we fix n and m and we consider that a is a variable, then we can see that this congruency has a D solution where D is GCD of n and m. That is, we can say that number of homomorphisms f from Zn to Zm is D, which is GCD of n and m. And what will be the form of those homomorphisms? So those homomorphisms are given by this. F of x is ax for all x belongs to Zn, where this a. Okay, so we will have d values of a. Uh, for those, we will have d homomorphisms from Zn to Zm. And what will be the values of a? Values of a will be the order of this codomain group, that is M, divided by the GCD of N and M into K, where this K varies from 0, 1 up to D minus 1. That is, the value of A will be multiples of M by D. Okay, and how many multiples? We will take these. That is, first D, non-negative multiples of M by D. Okay. So we can have a particular example based on this. So we need to find the number of group homomorphisms F from Z3 to Z9. See the solution. So we can directly find actually number of group homomorphisms F from Z3 to Z9 is GCD of N and M, which are 3 and 9 here respectively. So this is 3 and 9, and their GCD is 3. That is, we have 3 group homomorphisms from Z3 to Z9. And what are those homomorphisms? The homomorphisms are, so yeah, we will have f of x is ax, and here we have the values of a. So first will be f of x is a must be m by d k. So here this k varies from 0, 1 to d minus 1. And what is d? That is 3. And what is m? M is 9 here. That is, we have a will be 9 by 3 k, and k varies from 0, 1, 2. Okay. That is, this is 3 actually. So we will have 3 into 0, that is 0. This is the trivial homomorphism. Secondly, we will have f of x is 3 into 1, that is 3x. And next we will have, okay, for all x belongs to Z3. Here also we have x belongs to Z3. And then we will have 3 into 2, that is 6x for all x belongs to Z. So we have these 3 homomorphisms from Z3 to Z. Okay, I'm not erasing this. Let it be here. Okay. Next question is, find group homomorphisms F from Z10 to Z20. So first, what will be the number of group homomorphisms? So number of group homomorphisms from Z10 Z10 to Z20 is GCD of this is 20. GCD of 10 and 20, which is 10. So yeah, we will have 10 group homomorphisms. What are those? So the homomorphism f from Z10 to Z20 are given by f of x is ax for all x belongs to Z10, where a is, this is m by GCD of m and n. So this is 20 by GCD is 10 into k, or this is 2k, where k varies from 0, 1 up to d minus 1, that is 9. Means f of x is, you will have this meaning. 0x, that is 0, then 2x, 4x, 6x, 8x, 10x, 12x, 14x, 16x, and 18x. Okay, so here we have 10 homomorphisms. Now come to the next question. Find the number of onto homomorphisms from Z into Zn. So till now we have calculated the number of all possible homomorphisms. Now we need to figure out those are onto as well. So first we write the known result up to this point. So number of homomorphisms from Zn to Zm is GCD of n and m. Say this is D, and homomorphisms are f of x is ax, where a is m by d into k is 0, 1 up to d minus 1. And this is for all x belongs to G. Now we need to find like which one is onto, which one is not. So how to do that? So what does an onto function mean? Onto means in this group Zm, like under these type of function, if this Az which belongs to Zm, then every element has pre-image. Okay, so say if G belongs to Zm, then we have some B belongs to Zn such that that G can be written as B into X. Okay, that is under this function we can have pre-image of every element in this codomain. So it is equivalent saying that As one is a generator of Zn, then F is onto if f of 1 is a generator of Zm. Okay, that is if f of 1 generates Zm, then we say that f is onto homomorphism in this setup. That is f of 1 generates Zm, but we have seen that f of 1 is A, since f of x is Ax for all x belongs to Zn. So that is f is onto if A generates Zn. Okay, and we know that if A is a generator of Zn, then GCD of A and M, they are co-prime. So F is onto if GCD of A and M, that is 1. Now, uh, since F is a homomorphism, uh, by this previous result, we have that NA is congruent to mod M. NA is congruent to, NA is congruent to 0 mod M. That is M divides NA. Now, if GCD of A and M, that is 1, we get M divides N. Thus, F is onto if M divides N. Okay. So what is the condition for this homomorphisms to be onto? That this number M, this is a divisor of this number M. Okay. So we need to find the number of such homomorphisms now. So see, again, if M divides N, or let me write it directly. If M divides N and f of 1 generates Zm, then f is on 2. So number of onto homomorphisms is number of generators of Zm. Okay, that is number of elements of, sorry, this is Zm, of order m in Zm, because Zm is a cyclic group, and this is phi of m. Okay, so yeah. So how many onto homomorphisms from Zm to Zn? So first of all, onto homomorphism will exist only if m divides n, and if m divides n, then the number of onto homomorphisms will be phi of m. I would like to write it again clearly. Okay, so number of onto homomorphisms f from Zn to Zm. So this will be 0 if m does not divide, and this will be phi of m if m divides. Okay, because if m doesn't divide n, we cannot have any onto homomorphisms from Zm onto Z. Now, this is an example. We have these two groups, Z20 and Z10, and we need to find onto homomorphisms from Z20 to Z10. So, okay, what is number of homomorphisms? From Z20 to Z10, that is, what are the total number of homomorphisms? So that is GCD of 20 and 10, which is 10. And yeah, they are not same. Here we are considering homomorphisms from Z20 to Z10. Uh, Here we took homomorphisms from Z10 to Z20. Okay, they have same number of homomorphisms, but the homomorphisms are different because like the groups are different. Like here, which is the domain group, that is codomain group in this question. Okay, so and homomorphisms are f of x is, okay, this is again what we will do. A will be m by d k, and k varies from 0 to 9, right? And this time m by d, and m is 10 and d is also 10. So this will this ratio will become 1. Okay. So I can write it like this also. This is AX for all A belongs to Z10 and for all X belongs to Z20. That is all the 10 elements of Z10 will give homomorphisms. Now we have 10 homomorphisms, but out of these 10 homomorphisms, how many are onto as well? So, okay, since 10 divides 20, we ha have onto homomorphisms from Z20 onto Z10, and number of onto homomorphisms is number of generators of Z10, that is pi of 10, which is phi of 2 into 5, and 2 and 5 they are co-prime. So we can split it as phi of 2, phi of 5, which is 4. Okay. So we have 4 onto homomorphisms. So how to write them? For that, we will again consider the generators of Z10. So here we have um, like here this A can be any out of 10 elements of Z10, but if f of x is ax, this is onto homomorphism, then A can be generator of Z10 only. So now we list the onto homomorphisms. Um, Z20 onto Z10 are f of x is generators of Z10 means elements whose order are 10 in Z10. So we will have 1, that is x, and if x is a generator of Z10, then its inverse, which is this 9x. Inverse, this is 1 dot x, no? So 10 minus 1, which is 9. So 9x, this 9, this is also an element of order 10 in Z10. Then we have let me write it. F of x is 0, x, 2x, 3x, 4x, 5x, 6x, 7x, 8x, 9x. Okay. So out of this, we will collect those numbers which are co-prime with 10. That is this 1, 3, 7, and 9. 3x and 7. So this is what I was saying. This 1 and 9. They sum to 10. So if 1 is a generator of Z10, then 9 is also a generator of Z10. Similarly, 3 and 7, they both are generators of Z10. Okay. See, 2, 4, 5, 6, and 8. they are not co-prime with 10, so they are not generators of Z10. Their orders will be less than 10 in Z10. So if I will write orders, then order of 0 is 1, order of 1 is 10, and they all have order 10. And what is order of C? What are the possible orders? They are 1, 2, 5, and 10. Mm, that is generators of, that is divisors of 10 actually. So we have one element of order 1, we have one element of order 2, we have four elements of order 5, and we have four elements of order 10. So here, this 5, this is an element of order 2, and remaining elements have order 5. You can check. We need to add it into itself at least 5 times so that we can get a multiple of 10. Okay. So why I discussed this, because if we okay, I will explain this later with the help of a group of automorphisms actually. Okay, so this is answer. For on to homomorphisms. Now, as we found onto homomorphisms, we can also find one homomorphisms. So, how to do this? Again, homomorphisms from Zn to Zm are f of x is ax, where a is m by GCD of m and n into k, where k varies from 0, 1 up to GCD of m and n, or equivalently, we can say that NA is congruent to 0 mod m. Okay, so these are total homomorphisms. Now, F is 1, 1, that is a homomorphism is 1, 1. If and only if kernel of F is the identity. What is the identity here? That is 0. Then, by the fundamental theorem of homomorphisms, we have Zn by kernel of F. This is isomorphic to image of F, right? That is Zn by identity, which is isomorphic to Zn. This will be isomorphic to isomorphic to image of F, which is a subgroup of Zn. Okay, that is F will be a 1, 1 homomorphism if this Zm has a subgroup which is isomorphic to Zn. Zm has a subgroup isomorphic to Zn. Or F is 1-1 homomorphism if um, Zm has an element of order n. Okay. So what does it mean? Zm has an element of order n. Zm mm, can't have an element of order which is not a divisor of n, right? So this statement that Zm has an element of order n implies that n is a divisor of n. Okay. So this is same as Zm mm, divides n. It means um, for the existence of 1-1 homomorphism, this condition that n divides m is necessary. If n doesn't divide m, we can't find 1-1 homomorphism from Zn to Zm. Okay. If Zn divides Zm, then only we can proceed. So mm, this was the question of existence. Now, how many such 1-1 homomorphisms are there? So for that, we need to find the elements of order n in Zn. Okay. And number of 1-1 homomorphisms from Zn to Zm is number of elements of say, number of elements of order n in Zn, which is pi of n. Okay. So I can conclude it as number of 1-1 homomorphisms from Zn to Zm. This is 0 if n does not divide m, and this is pi n if n divides n. So this is a question where we are to find number of onto homomorphisms from Z4 to Z12. So first we see that 4 divides 12. So there exist mm, onto or 1-1. Okay, actually here 12 doesn't divide 4, so there is no onto homomorphism. But 4 divides 12, so we can find 1-1 homomorphism. Actually, yeah, the question was to find number of 1-1 homomorphisms. This is a typo, but yeah, we answer for both 1-1 and onto. So how many onto homomorphisms? 0. And how many 1-1 homomorphisms? So that will be, let's find them. Number of 1-1 homomorphisms is pi of 4. See, in case of onto homomorphism, so we take phi of order of the 4-domain group. But in case of number of 1-1 homomorphisms, we take phi of order of a domain group. Okay, so this is the difference. Because in case of onto homomorphisms, order of this group divides order of this group. And in case of 1-1 homomorphism, order of this group divides order of this group. So this is the basic difference. So order of 4 is, sorry, phi of 4 is 2. So we have only two 1-1 homomorphisms. And see, total number of homomorphisms, they are GCD of 4 and 12, no? That is 4. That is, we have 4 homomorphisms, but out of them, only 2 are 1-1, and no one is on. So, okay, fine. Let's list them. Homomorphisms from Z4 to Z12 are f of x is ax, where a is 12 by GCD, that is 4, that is 3 into k, and k is 0, 1, 2, and 3. GCD minus 1, right? So this will be 0, 3, 6, and 9. Okay, so these are homomorphisms. Okay, and orders of these elements. So order of 0 is 1. Order of 3 is 4. Order of 6 is 2. Order of 9 is 4. Therefore, see here, what we have done. We found the number of 1-1 homomorphisms by the number of elements of order n in Zn, right? So that is here, we find the 1-1 homomorphisms by the elements of order this 4 in Z12. So these orders are calculated in Z12. So we have these two elements of order 4 in Z12. So excuse me. So f of x is 3x and f of x is 9x. These are 1-1 homomorphisms. From Z 4 to Z12. Okay. So this is the next question. Now we need to find the number of automorphisms. See, till now we have discussed homomorphisms, 1-1 homomorphisms and onto homomorphism. So if a homomorphism is 1-1 and onto as well, then the homomorphism will become automorphism. And in that case, Zn and Zm, they both must be same. Okay, like this. So here we need to find f from Z8 to Z8 such that this f is an automorphism. So what is number of homomorphisms or the number of endomorphisms? Got confused, so let me write it. Number of homomorphisms is this is GCD of 8 and 8, which is 8, obviously. So we will have 8 homomorphisms or 8 endomorphisms from Z8 to Z8. Now, see, since like these two groups, Z8 and Z8, they are same. So if a homomorphism is 1-1, that will be onto and vice versa. So since 8 divides 8, that is order of this group is a divisor of order of this group, and order of this group is a divisor of order of this group. So there exists 1-1 and onto homomorphisms also. Okay. And 1-1 and onto homomorphisms are same. Okay. So this is about the existence of automorphism. Now, what is the number of 1-1 homomorphism? So let me write it. Number of 1-1 homomorphism, which is same as the number of onto homomorphism, which is same as the number of automorphisms here. That will be phi of n or phi of m because both are same. So this will be phi of 8 here. Okay. What is phi of 8? That will be, let me write it how to calculate it. This will be phi of 2 cube. So this will be 2 cube minus 2 square, that is 8 minus 4, that is 4. So we have 4 automorphisms. Now we need to list them out. So see, if this is asked to list all the homomorphisms, then they will be f of x is ax, where this a is any element of z, because we have exactly 8 homomorphisms there. Okay, so this is not difficult to list all the homomorphisms, but I'm listing the automorphisms here. Homomorphisms you can list. So automorphisms from Z8 onto Z8 are f of x is okay. So here what we will do, we will write this as AX, where this A is an element of order 8, or an element which is co-prime to 8. So this will be 1 plus X, and then we will have 7X also, and then we have 3X and 5. Okay, so mm, automorphism group of Z8. This is actually uh, F from Z8 to Z8 defined by f of x is ax, and such that a is 1, 3, 5, and 7. What I wanted to do here is mm, a, or I can explain what I was trying to with this question only. So here we need to find automorphism group of Z35. So what is the order of AUT Z35? This is phi of 35, which is phi of 5 into 7, which is phi of 5 and phi of 7. So this is 4 into 6, or this is 24. That is the order of this automorphism group of Z35, that is 24. Now, what is this up to isomorphism? So we can say that automorphism group of Z35, this is isomorphic to the mm, unit group of Z5 cross unit group of Z7. Because Z35, this is isomorphic to Z5 cross Z7. See, this is isomorphic to Z4, and this is isomorphic to Z6. The automorphism, Automorphism group of Z35, this is isomorphic to Z4 cross Z6. So whenever you need to find the automorphism group, you can find the group of units there. Okay. Okay. So how to do this here? See, what is unit group of Z8? That is this elements 1, 3, 5, and 7. Okay. Here the operation is multiplication modulo 8. So if we want to find order of these elements, so order of 1 is 1, because 1 into 1, like, or we can say 1 to the power 1 is 1 modulo 8, because here we are taking multiplication modulo 8. Order of 3 is 2, because 3 into 3, that is 9, which is congruent to 1 modulo 8. Order of 5, so 5 into 5, that is 25, which is congruent to 1 modulo 8. So this is 2, and order of 7, that is so 7 into 7, that is 49, and order of 7 is also 2 in, you can say, UZ8 multiplication modulo 8. Okay, because 7 into 7 is 49, and that is also congruent to 1 modulo 8. So there is no element of order 4. And here, order of UZ8, that is 4, but it doesn't have any element of order 4. So this will be isomorphic to unit group of Z8, which is isomorphic to Z2 cross Z2.